Hello, everybody, and welcome to episode 83 of the Hyperthesis podcast. I'm Liam.
I'm Patrick.
I'm Pheely.
All right, so I apologize immediately for my microphone quality today. I'm in my office and I forgot to bring my microphone with me, so I'm just using my laptop microphone. So we'll see how that goes.
Shame.
Yes, I know.
Shame.
Great shame. But today we're going to be talking about space and space exploration and things like that as our main topic. But until then, I'd like to talk about my conference experience. So last week I was at the CAP conference, which was held at Western University in London, Ontario. And CAP is the Canadian Association of Physicists, for anyone who doesn't know. And every year they have this annual congress. So it's basically just a big conference somewhere in Canada where, all these Canadian physicists come together and talk about their research. So it's a whole bunch of different areas. There's not really one specific target area, which is kind of nice. So you get kind of like a general overview of the physics that's happening in Canada, which is nice. And it's nice because it's not quite as serious. Like if you go to a more specific conference, you have to be a bit more careful because most of the time the people that you're citing in your posters and your talks will be there. Like when I went to Italy, like all the people I'd been citing were there, and you have to be very careful not to basically make them angry with you because if you accidentally don't cite them or you cite them for the wrong thing or you misinterpret their results, they will tell you. Whereas CAP, you could go present your work and not as many people are going to be aware of the literature and what you do. So my group went, so Josh and Denise were previous guests on this podcast. We all presented our work, and my supervisor went and presented his. It was pretty fun. Dean was there, who was one of our previous guests. He was actually presenting some work on a paper that me, him, and Pheely and two other people submitted. And he won some big awards for it somehow, which is, I heard his talk. It was a good talk. But the subject that the paper was on was pretty niche, and I was quite surprised that the judges were so into it. So Dean, good job, man. You really convinced them to like that work.
Well, they say it's the chef, not the ingredient, Well, which I disagree. But, they really let him cook, right? So I didn't hear his talk, but it must have been really good to sell that because what we did was very theoretical. Actually, almost it is a mathematical proof, right? So if you can sell that, you can sell anything.
Yeah, and I just want to shout out Dean for getting the honorable mention within the finals. Really well done with that, and definitely shows good science communication. And you should definitely go check out our episode with him, which will be posted in the description below.
Yeah, exactly, Pheely. The paper is just a mathematical proof, which we worked on it during our undergrad with a professor who unfortunately passed away, and we came back later to finish it. But it's one of these super niche papers that if anyone who knows what they're talking about in that field would look at the paper and probably think, yeah, okay, but so what? And that's kind of how I feel about it. We wrote the paper ourselves, and even I think it's worthy enough to be a paper, but I don't think it's like this. I don't think it's life-changing, I'll put it that way. It's interesting, but it hasn't, I'm surprised that the judges really liked it that much. They're not really, they're not fully judging you on the content of your research. that's part of it, but they're also judging you on like how good you are at talking and communicating and all that. I got to take a look at the judge rubric actually, um, and I think only like 20% of it is like convincing them that, or 20% of it is convincing them that your research is important. So even if they think your research is 0% important, you can still get like an 80% score in principle, I guess. But I think he did a pretty good job of convincing them. So it's kind of nice that I guess this is the first time I've been involved in a paper that someone else has presented, and someone else has presented and done well in as well.
I think it's worth definitely talking about that paper sometime, even getting Dean back on here and having you guys discuss it. But in terms of CAP itself, were there any interesting presentations that you saw that really stuck out to you, aside from, of course, Dean's presentation?
Oh yeah. So let me think. So this year, the problem is that I was only there. It's okay. The CAP conference was a week long. It was from Monday to Friday, and I was only there Monday and Tuesday because Hamilton, where I'm at, is quite close to London, Ontario. So we just drove down, stayed a night, and came home the next day. So I'm sure there was a bunch of talks I missed, but on the Tuesday that I was there, there was a lot of interesting talks. And for me, when I say interesting, I mean like all the black hole and quantum-y talks. And there was one session. So the way they do it is there's all these parallel sessions because there's too many people to present one at a time. So they have to have a bunch of people presenting at once in different rooms. And you just kind of go to whatever ones you're most interested in. And there was a topology and holography session, which I thought would be completely abstract. In my mind, when you say topology and holography, I think you're talking about like, you know, cosmology and maybe even like condensed matter physics. But all the talks were on like the Unruh effect and things like that. I was kind of surprised by that actually. I'm not really sure what that was about. But there's this really popular physicist named Robert Mann at the University of Waterloo / Perimeter Institute, and he's this massive name in black holes. You know, he publishes like once a week or something crazy. It's ridiculous. So I've met him a few times over the years because I'm so close, and you know, he was at my talk and he asked me a few questions. But this holography session, there were 6 presentations and 5 of them were his students. So it was kind of interesting, but it was good because I took this class that was called QFT and Curved Spacetime a while ago, and there was stuff popping up in there that I don't really use, but I was like, oh, I actually understand these talks, and there was a really interesting talk by a woman whose name I forget, but she was a Robert Mann PhD student, and it was on how if you're falling into a black hole, you can use a qubit to kind of actually detect, like as an early warning system. So if you're falling into the black hole, you probably aren't able to see where the horizon is, but you could have this qubit detector, and it can give you a signal that tells you you're approaching the horizon before you actually hit it. So it's like an early warning system for falling into a black hole, and it was all the theory behind that. And I thought that was pretty cool. I mean, not that we're ever going to be near a black hole anytime soon, but it was a really good talk, in my opinion.
Well, it's gonna be funny because time stretches a lot by near the event horizon, right? It's like, oh yeah, we received a warning, but from people outside, yes, that you were there for 500 years, buddy.
Yeah, and I guess it depends on how big the black hole and all that. Like, there's a whole bunch of things it depends on. You'll get the early warning system, you'll escape, and you'll return to your planet where nobody's alive anymore or something.
So how is the what do the kids these days call it, the vibe check of the DubCap conference now, or congress?
Oh yeah.
Now would be worthy of what do you call the internet influencer to do a vlog there.
That was a lot of words you just said. I was only there for 2 days, but it was good. There was a couple weird decisions in my opinion. So they had the conference was held in 2 buildings, and you kind of had to go between them. So some of it was held in like the physics building, and some of it was held in the social science building, and they're pretty close to each other. But for some reason, they had the poster fair split up between the two buildings, which was a strange choice. And the other thing is that they didn't provide lunch. They provide lunches if you book them in advance, but I think most conferences will just give everyone lunch. Typically, they don't, they don't say like, here's your assigned lunch for the day and here's your assigned lunch. So I kind of forgot about that and I didn't book any lunch, so I had to go adventure for Subway or something during the lunches. And but like overall, it was quite good. It was pretty well organized. My other, I guess I'm only saying negative things right now, even though it was a really good conference. But my talk was on analog gravity, and they put me with all like the hardcore GR people. So I took it upon myself to make it like an introduction to analog gravity talk, which, I think there was no way they were ever going to consider me for a prize because I was just in the complete wrong presentation. It's like what happened to you in 2022, Pheely, right? Like the same thing happened to me, but like it was a really, like, the talk went pretty well. And there was a lot of really good questions and people were pretty interested in it. So the vibe was good.
Well, I mean, maybe you're too used to the European hospitality of the good food in Italy and Patrick in Spain. Well, I mean, conferences I find in North America are a little lacking in that aspect. Well, I mean, North America is lacking in that aspect. Changed my mind.
I agree.
Absolutely.
So
actually,
I guess it.
slightly disagree. Your physics conferences, maybe.
Yeah, okay. Anyway, yeah, it was a good conference. Congrats to Dean. Good job to all the other people who presented. There were some really good talks. Yeah, we'll see. I don't know where's next year's gonna be. I don't know.
Cap is very small, right? Only a few hundred attended the conference usually, or maybe 1,000 max. Do you think it's more than 1,000?
No. Really? Okay, Patrick might think so.
I mean, in the past, Cap, it's the biggest physics conference in Canada. It's just so general. So I would say there's over 1,000.
This year, there definitely was not anywhere close to 1,000. I'd say like 400. I'd say like 500.
Cap might have more than 1,000 members, but I don't know how many would attend, right?
Although next year it is in Saskatoon, Saskatchewan.
Okay.
At the University of Saskatchewan.
I've never been to Saskatchewan, so I'll probably end up going.
Come visit me in the prairies.
I want them to host it a little later when the CFL, Canadian Football League, is on, because I want to go see the Rough Riders, the Saskatchewan Rough Riders. Everyone love them.
In Hamilton, everyone loves the Tiger Cats because that's Hamilton's CFL team. Anyway, though, yeah, it was a good conference. Got to catch up with some friends I haven't seen in a while. Got to present my work, which is always nice. And we'll look forward to the next one.
Well, have you met anyone from Queens that I know?
I don't think so. I could have, and I just didn't realize. I met a few people from X, and did I? I thought I did, but maybe I didn't. I guess Dean. He was the only one from X.
You're a little confused, Liam. What is going on here?
I get the problem is that all of the caps I've attended in my life just kind of blur into one big event for some reason, and I always forget which is which, even though it was last week. So I'm like, was Michael Steinitz there this time, or was it last time? I can't remember which one it was. Yeah, I think it was last time, but yeah, it was good. So to move on to our main topic now that we've talked about the CAP conference a lot, I believe Patrick has something to tell us about. I don't want to say interstellar travel. Maybe it's just intrastellar travel, but he has some space things to talk about.
Yeah. So for today's main topic, with a lot of recent news happening in space exploration, I thought it would be fun to talk about what's going on in space. I mean, we've talked about rockets before. We've also talked about different probes that are around. But as the general topic of space exploration, that's something that we haven't really delved into. But I think it's really interesting and is becoming increasingly important. as we start to have cheaper and cheaper space launches, and we are sending out more and more into both the intrastellar system, so our solar system, as a normal person would word it, as well as looking at possible missions that are interstellar. So figuring out how we can send probes, for example, to different star systems, such as Alpha Centauri, which is the one that's closest to us at only 4.2 light years. There's also a really rich history of space exploration, part of which will be discussed by Pheely later on, I believe. But yeah, I just want to delve into like what's going on in space right now and what are some interesting things that are popping up. And so to start, I'm sure a lot of you are listening to this have seen, at least in the news at some point, that, oh, there's another probe landing on Mars, or, oh, we reached out to Voyager again, or a really common one, probably about 10 years ago to 15 years ago was, oh, the Voyager probe, especially Voyager 2, has reached the edge of the solar system. And then a year later, oh no, it's actually reached the edge of the solar system. And then a year later, it says it again. We're pretty sure it's outside of the solar system now. But there's a lot of cool things going on and a lot of very interesting probes. And the other thing is a lot more countries are getting involved with their own kind of space systems. So traditionally, we have the United States and the European Union and Russia, of course, which have been dominant in space. But now we're seeing smaller countries like Japan and China and India all sending different probes and rovers and missions into space and surrounding bodies.
Feels wrong to call China, Japan, and India smaller countries.
I should say smaller in terms of space programs. Yeah, that I was like, oh yeah, Japan's smaller than the United States, but definitely not China and India.
You're talking about a quarter of Earth's population or more.
Yes, yeah.
Just from China and India alone, right? That's like 2 billion.
Yeah.
Actually, past Japan.
Even more. I think it's 3 billion. That's like 3/8 of the population.
Yeah, so it's interesting that they're catching up in the space. I don't want us to call it the space race because that's old news, but they're catching up in the modern day space race.
So it's good that you did mention the space race because that's where all of this started, was in the 1950s and 60s when, during the Cold War, the United States and Soviet Russia, or the Soviet Union, were competing to see who could make the most advancements in space. And of course, that had applications for claiming territory, which didn't actually happen, but also for the development of other systems like ballistic missiles or spy satellites. So this really was all kicked off by the Russians, of course, in 1957 when they launched Sputnik 1. And that was the first satellite in space, and it was sending out radio signals that could be measured anywhere. And based on its speed and its position, you could easily tell that it was in space. Of course, the Russians also were the first to send a person up into space with Yuri Gagarin. And then later on, the Americans were the first to land on another body other than Earth, which of course was the moon landings in 1969. So these are pretty landmark achievements. But since then, we've seen so many developments, including we landed multiple different missions, the Apollo missions on the moon. We haven't sent someone back since, which seems kind of crazy. But now we are planning moon missions with the Artemis missions, and we are even trying to get Mars missions started, which, if you've ever read the Red Mars series, allegedly it was supposed to happen in 2020, but that kind of fell off by a lot.
There's not really a need to send people to the moon, right? Like, what are we going to do there? Because if you send scientists there to collect rocks and stuff, well, the probes can do that, robots can do that. So in a sense, it's unnecessarily expensive. I think the reason we sent it back then, because we never did, and also it was like for fame, or what young people call it, clout.
I would disagree with that. I think it is important to send people to the moon so that we can test out survivability in extreme habitats. It's kind of like sending people into like the barren wastelands in northern Canada, especially Devon Island, to try and figure out how we can survive on Mars. If we have people on the moon, which is a lot more irradiated by solar radiation and other dangerous ionizing radiation, then we can discover, okay, what works best on the moon and how can we implement that, say, in interplanetary spaceships or even in different projects that relate to different further afield. So it's a great testing ground, if anything.
Well, there are two things. First, you can do that in orbit because the moon doesn't have atmosphere. There's almost no difference except for the little bit of gravity they had. And I don't think the missions they're sending, they're not living on the moon, are they? They're just hanging out there for a little bit and come back. I think living on the moon, we are quite far from colonizing the moon. Well, not that far. I think if we spend a lot of resources and convince a lot of people or people in power to do that, it would be possible. But I don't think there is any, significant benefit to basically being on the moon right now, unless we're trying to basically build a moon base or like a big one.
Well, I think the purpose is partially to build some sort of moon, not necessarily like base, but some sort of temporary, at least, settlement. But if you think about it, we haven't really sent people beyond low Earth orbit for 50 some years now, 53, I believe. And so the fact that anyone who's working at NASA was not there when we were sending people to the moon, technology has advanced greatly. So if we are trying to send people to Mars, then a first stepping stone is figuring out how we can get to the moon. And there's a really good video by Destin from Smarter Every Day, where he actually gives a talk to the people who are planning these missions and saying, okay, we are in a different time. We have different technologies, and you really have to think about, one, why are we going to the moon? Which is a really valid question. But the other major point he makes out is, how are we getting there? And how is the planning somewhat almost flawed from the start?
Yeah, I was going to say, I think you can make the argument that a good chunk of modern day science, there's no point to do it in terms of getting an immediate reward out of it, right? You're doing it because, 50 to 100 years from now, it'll be useful sometimes, or things like that. So, I mean, you can come up with any argument like, oh, what's the point in doing this? It's just a waste of resources right now. It's like, well, sure, but that's not the point. The point is that it won't be one day, hopefully.
Well, the moon is not exactly a good place to habitat too, right? Because lack of atmosphere. I mean, look at how many holes are on the moon. Well, one day you're gonna have a stray bullet from the star just hit you. Well, I mean, you probably can see that from very early on, but I agree that it's a good stepping stone for like a longer interstellar travel, right? If you want to go to Mars or further, well, if you can't really go to the moon, well, back and forth, well, why are we trying to go to have a long-term or constant communication or transport to Mars if we can't even do it to the moon?
Yeah, and like Patrick said, I think if you actually talk to the people who plan these missions and are going on them and stuff, and you say, what are you doing up there? I think they're going up there and they're doing a lot of stuff. They're not just prancing around taking photos. They're doing a lot of science and things up there and trying to learn and figure things out for the future. And so it's not quite a complete waste of time, I'd say.
And I mean, there are resources on the moon. So the moon has a similar composition to the Earth. And so if we can study the resources and understand what's up there, especially for future technologies, like there's a lot of helium on the moon, especially helium-3, which is incredibly useful for fusion reactions. Of course, we don't have any active power-producing fusion reactors yet, but there has been quite a lot of progress in fusion. So if you can make things like helium or extract helium from the moon and figure out ways to do that, and of course, humans are able to improvise, whereas robots, not necessarily. So I think knowing the resources that we have available is also important.
Helium's also, well, I forget which type of helium, but helium's expensive these days because there's a finite amount. So more helium is always good.
Well, maybe once the fusion reactors comes online, we will have a lot of helium, right? Because
Yeah.
and also, I want to point out that you said, technology is different. I think now is even more efficient to not send people and send those remote control robots to do those tasks because how advanced we can do it now because humans have a lot of limitations, right? Although we can be more adaptable in certain when you think and stuff, when we want to have some humans to basically fine tune things. But I think these days, since the moon is not that far, you can do it remotely. And it's even better to send robots on the surface because they don't require food nor, get really affected as a living being by radiation and such. So in a sense, in the term of like resource extraction and stuff, having humans there are quite inefficient because in a way living beings, living organisms are not really made for it, and we're gonna struggle to do that. But I can see why some of the part of the missions may benefit from humans being there and fine tune things or change things there. But these days the advancement in telecommunications allow these tuning and changes to be done remotely or send another probe or another robot to do it, and they are much more precise than us. I know we have the CNC machines to do all these cutting and building stuff, and they're much better in a sense for like efficiency. They might look too perfect, right? Too not handmade, but objectively they perform its task very well. I mean, it's designed to do so.
Yeah, but at the same time, sometimes these rovers get stuck on a rock.
Well, sometimes humans die.
True.
They get sick.
Anyway, well, I guess moving on to rovers, especially ones on the moon and Mars, that's our current state of space exploration. We haven't sent people up to Mars or the moon yet, or in 50 years, respectively. But we certainly do have a lot of different robotics that are on these places, whether it's a probe orbiting the moon or Mars or the sun, even with the Parker Solar Probe. We do have a lot of robotics, and they're quite advanced. We just had Perseverance launch a couple of years ago and land on Mars, which joined Curiosity. And we even sent a little helicopter to Mars. The Ingenuity, I believe, was the name of the helicopter. So we do have quite a few of these different probes that are doing a phenomenal job. And one thing with the Perseverance rover that I really want to focus on is the Mars Sample Return Project. So this is a really exciting project that actually a professor in my department is helping work on and someday wants to coordinate. But he essentially, this whole project is the Perseverance rover that's collecting samples of Martian soil and components within that, and then essentially leaving these sealed tubes on the surface of Mars to be one day picked up and returned to Earth. So we hope that one day we can actually return these samples to Earth, study them, look for biotic components or possible chemicals relating to life. But that's a really exciting not adventure, but that's a really exciting opportunity to learn more about another planet. Because of course we have moon samples. We just recently had samples returned from an asteroid, which they had difficulties opening. But having samples from an actual other planet is quite exciting.
Yeah, I think we talked about that a little bit or mentioned it that, scientists were try to be very careful to open in that capsule, right? Because you don't want to have contamination or things on Earth on there. And when you try to go detect, oh, what's in there? Like, oh, they have same stuff we have on Earth. But what happened really could be that the contamination got in from Earth. So you have to be very careful how you open that up.
And just to put a name to it, that was the OSIRIS-REx mission, which returned samples from the Bennu asteroid. But going even further afield than Mars, which we have the Mars Reconnaissance Orbiter, we have many different rovers there, and we even had the Phoenix lander landing in the polar region. That one, of course, did not last as long because it was in the polar region, but that was able to look at the ice on the polar region. But moving further afield, we have probes like the Juno probe, which was orbiting Jupiter for quite some time before gloriously crashing through the atmosphere of Jupiter. We also had Cassini, the Messenger probe, which was designed to monitor Mercury and different aspects of that. We have the Viking probe that was sent to Venus. We have the Parker Solar Probe, which I also mentioned, which is actually trying to and is orbiting the sun within the corona, which is incredible. So we're actually getting data about essentially what's inside the sun, or at least the sun's atmosphere, in quotations. So there's a lot of exciting exploration going on just within our solar system itself. And we are receiving a lot of interesting data. But looking further afield still, we've sent out some interesting probes out. So, of course, we have the Voyager 1 and Voyager 2 probes, which were sent out also in the 70s. Lots of good things happening in the 70s for at least space exploration. But this was the first time that we were able to really see what was in our outer solar system with these different probes. And of course, these were launched in the 70s. We will hear more about the Voyager a little bit later. But another probe that was sent out more recently was the New Horizons probe, which again passed by some of the outer planets in the solar system, a notable one being Pluto. So we actually have high definition images of Pluto. We know a lot more what it looks like. It, of course, has the heart on the side. I believe that was about 10 years ago now that we start seeing pictures of Pluto. And that's still on its way out and will eventually go out of the solar system as well.
I think that's really a good example of why you should always keep exploring, because before that, I think people were pretty sure that Pluto was just this pretty barren place with not much going on. And then when the spacecraft flew by and, the satellite flew by and got the photos, they realized, like, wow, there's way more to Pluto than we ever thought there was. And that's usually the case, everything's more, a lot of things are deeper than you usually realize at first. But I think it's like the same as the James Webb. With the James Webb telescope, they're realizing like so much that beyond what they could have even predicted. It's the same with Pluto, so that's always really cool to me.
Well, to be fair, our vision or our range of perceivable light are quite limited, right? And we are biased because we're humans. We believe that, these are the colors, these are lights that form colors. But as we know, electromagnetic waves comes in a much wider range of frequencies. And with James Webb, for example, they look in infrared, right? So you see basically a different universe, and it opens up all new doors and windows to look into the universe. And we looked in IR before, but not as this high of a resolution that we did with the James Webb telescope. So I think in the next decade or so, there's going to be new discovery, new nature that we weren't really able to perceive before that could give us some ideas of what the actual nature behave. But it could be a dot, which I don't think it will be, but that's the nature of research, right?
Yeah, even the quantum gravity people, they're hyped about the James Webb because even like a year or two, or even just like a year after the James Webb was, fired out and running in space, there's just all these papers coming out from the quantum gravity people being like, maybe this, like they're trying to modify and solve quantum gravity, right? And the more experimental evidence you have, the easier it is to do. So they were all pretty hyped about that.
And speaking about James Webb, the Hubble Space Telescope, along with the Kepler Telescope, Spitzer, there are all these great telescopes that are being used to do essentially space exploration further afield, where we can't send probes and astronauts yet. And so it's thanks to satellites that orbit the Earth, like the Kepler mission, which were able to detect thousands of exoplanets, showing that yes, there are other worlds there. And now with the James Webb Space Telescope, it's incredibly exciting because for some of those closer planets, we can actually look at some of the infrared light that's transmitting through their atmosphere and trying to determine what the atmospheric composition is. So it's really quite incredible the power of especially an infrared telescope.
Well, I think one of the good feature of electromagnetic waves is that different frequency can penetrate different materials, right? So sometimes you have dust or cloud, well, not cloud, but kind of gaseous clouds in space where it's opaque to visible light. So like, well, we don't know what's behind there. We don't know what's in there. But maybe when you go to infrared, you can unveil it, seeing through it, and it really opens up new possibilities, right? Well, it's like how we can't see our bones, but we go to the doctor. They use X-ray, which is another form of light, but they can go through the skin, but not the bone, so you can see the structures of the bones. So in that sense, analogously, we are doing that to the space. I think we also receive both X-ray, IR, UV, any other than visual light, which we already do, right? To really maybe can we see through certain veils that space has.
Yeah, so it's really you can compare, like you can even take the James Webb photos and the Hubble photos, put them next to each other, and see that exact thing. You can see in like the Hubble in the visible spectrum, might look like a bunch of dust, but in the Webb you can like see through it and see all these massive stars and things behind it that you couldn't see before. So having different spectra to probe through is always very good.
So it's really interesting because like a lot of these probes, they're essentially remote sensors that are able to detect things, especially in say planet atmospheres or the atmospheres of moons and planets. So we're sending remote sensing satellites to different planets. And I mean, like you said, it's all dependent on electromagnetic radiation and how it interacts with matter because it interacts with different types of matter differently. So there's really a lot we can tell just by sending up a simple probe and figuring out, okay, how's light reflecting or transmitting or being absorbed by the atmosphere. So really a lot of cool things. And it's just fun that there's a lot of crossover with my field just because if you're a remote sensing scientist, you can work in space or on Earth.
Well, one thing I like to think about for space exploration is the scale. Because we kind of can tell roughly how big our planet is, and also as a personal experience, right? A human being only see maybe a few kilometers far, and we know the Earth has like it's pretty big, right? It's like the radius is probably like 6,000, was it, kilometers, which are huge,
Yeah.
and we are sending this probes out into space, but these probes are tiny. if you compare to the size of the celestial bodies that we have, it's like if you take a photograph of Earth and Moon, right? You won't even see any satellites or space stations. They are like smaller than a grain of dust. And we are using these grains of dust that we made to send into space that and capture all these massive celestial bodies and you can have galaxy and such. But the sheer size of the scale, I think, is almost unimaginable. Where I don't know if someone's go to like the Grand Canyon or the big mountain range to Rocky, you can feel that the sense of sublimity, right? Where all these feelings of being small, but that doesn't even compare to, let's say, the sun, Jupiter, right? Those are so large. When we see in the photographs, we think they're like, all right, they're just a little ball, all right, a little sphere. What's the big deal? But if you compare to the size of Earth or the size of human experience, I don't think one can really have have a feeling for it. Maybe that's why people would say when you go to space, look back at Earth is really overwhelming.
So I do want to focus on the small just as a kind of final thing, because small, even smaller than, say, the space station and the grand scale things, is massive compared to a project that's being worked on known as the Breakthrough Starshot. And so this project, which was founded in 2016 by Yuri Milner, Stephen Hawking, and Mark Zuckerberg, so a rich guy, a famous scientist, and I believe Yuri Milner is also an investor physicist and a couple other things. But essentially what they're planning to do is to make very, very small probes. So essentially just microchips that are, of course, well protected for the harsh environments of space, have solar sails on them, which of course will still be quite small, put them into orbit, and then launch them towards Proxima Centauri using a laser. Because if you have a high-powered laser and a solar sail, that's a lot of momentum that's being transferred to this device, and it's small enough that it accelerates quite quickly. So by shooting a high-powered laser at the solar sail, it's able to accelerate and essentially make it to Proxima Centauri, mainly within our lifetime. And so this is a very exciting project. It, of course, requires quite a lot, but it could be a very interesting way by sending a lot of these different probes to actually see and visit another solar system in a reasonable amount of time at a decently reasonable cost.
Well, the fortunate thing is that space has no air, so very, very little resistance, right? So even though you increase momentum by a little bit, or increase is good, because if you have it in normal air that we have on Earth, it's gonna slow down. It's like how people were in water, right? You try to accelerate, you have to send a lot of force, and if you maintain your speed, you're slowing down because the fluid actually drags you back. But in space, even you use a little bit of light, well, not a little bit, a decent amount of light, you can generate momentum. It will keep going, which is great. And also the timeline of these projects are, beyond lifetime sometimes, which is in a sense heartbreaking because imagine to be a person who worked on it. It's like, well, we are sending this and good luck, man. You're gonna have your grandchildren and we probably start having your first data from there. Or it would start going to phase 2. So the time scales of these are very long. So you have to be prepared for things that could happen. And lucky that the probe we made don't have organic material or life, that they're block of metals and non-metals and bunch of stuff which don't really change that much over hundreds of years, hopefully. So in a sense, that's pretty good. Better than sending people and living beings because they're not gonna live very long.
Absolutely. And just to put a couple numbers to those figures, so they'd be accelerating at 100 kilometers per second squared. So pretty fast. So they'd be able to get up to their target speed in about 10 minutes. And it would be about 1 terajoule of energy delivered to each sail. And they want to make 1,000 of these, each with a 4x4 meter sail. But of course, they only weigh a couple grams. And the plan for this is to have a square kilometer array of 10 kilowatt ground based lasers with a combined output of up to 100 gigawatts. So, yeah, it would take about 10 minutes to get to that terajoule, and it would just be quite the project. That'd be quite the laser setup, too.
Or I have an idea. I probably gonna do this at some point to start an original idea, for sure. Send another probe, go near the sun. Maybe not that near, but it's like a laser station, right? You convert the photons from the sun, create to a laser, and use that to propel your auto probes or auto spacecraft. Because in that sense, you almost have like infinite power as long as the sun goes still alive. And the sun is a massive fireball, right? If you can convert even a fraction of that energy into lasers that can propel your ships, that's gonna be like people think of the moon creating like a fueling station at the moon. So there'll be the light fueling station by the sun. So that's gonna be pretty cool.
Yeah, I think in like sci-fi, I've heard of ideas like this before, where you make this array of like big solar panels kind of around the sun or near the sun, and then you transfer that energy to Earth with lasers, or you transfer to another station that's in between the Earth and the sun, and then that station transfers it to Earth just by firing lasers between each other, which could be a really interesting way to help with energy. I mean, I don't know how realistic that is. Probably not realistic at all, but who knows?
In a sense, could be pretty clean energy, right? Just from the sun, it's as clean as it can be, and just lasering to the earth. And also losses, we don't care that much because the sun, we have a lot of energy from the sun. But I think the problem is to like how is the probe or the station is going to survive being bombarded by all kind of radiation all day, all the time.
Yeah, and the other thing is, can you create a laser that shoots such high intensity, high focus light continuously all the time without it kind of falling apart and breaking after a while?
Well, maybe it doesn't have to be lasers. It has to be just some light, right? Like, because if you don't care that much about directionality, just have some directionality, like lenses just focus light. Maybe you'll be the pioneer because caustics and whatnot to create some kind of arrays of lenses that focuses on Earth. It sounds kind of risky. It's like, well, we made a mistake. We burnt Earth. Oops.
It'd probably be with lasers. That's probably a safe bet. But
Yeah, probably like multiple lasers because laser is monochromatic, right? And we want to harvest everything.
I mean, the sun's giving off enough energy. You probably don't need pure white light. You could probably just do one and it'd still be plenty.
Yeah, well, I guess we'll see. I mean, in the future, I can imagine we're gonna be doing something like that to have infinite energy, at least for us, in the scale of human life, right? Nuclear now is going really well, but imagine the orbital laser for energy. That would be so cool. Not to kill bugs and stuff like in some video games.
Well, thank you very much for that topic, Patrick. And then for Pheely as well for all the very interesting ideas and discussion. Yeah, that was good. Sorry, I got distracted because there's this pod. So this is a Cap story actually. At Cap, they have like you know how they have graduate fairs at some conference, at undergrad conference, where all the universities have like a table and you go to them and they'll try and recruit you to grad school. At CAP they had like an experimental fair. It wasn't titled that, but effectively there was all these tables and it was just companies trying to sell you their vacuum pumps or their specific like circuits or things that you would need in labs, their lenses or lasers or things like that. And there was one guy, and I think he was selling vacuum pumps or something, but he has this he was telling me about his podcast, and I was like, "Oh, I have a podcast." So I was just looking into that right now, and maybe there's some potential for collaboration. I don't know.
Well, I mean, if you sell vacuum pumps, maybe you sell like, well, this is the ultimate pickle maker because you can make pickles in seconds if you have vacuum pump and little chamber.
That's a nice little experiment you could do if you own a vacuum pump. I don't know if he was selling vacuum pumps. I didn't really check, but some of the tables nearby were, and there was people selling like life insurance too, which was kind of weird. I think they just pay the conference to come and advertise their stuff, so the conference has money to spend on things. But anyway, moving on, we have a very potentially, depending on how well Pheely tells us, interesting story on Voyager. But before then, Patrick's going to tell you how you can reach us. And we are not so far away. We're actually on the Earth, so you don't have to develop space travel for that.
Absolutely. And I mean, you don't have to try and sell us a vacuum pump either. But if you'd like to talk about vacuum pumps and the science of vacuum pumps, or if you work with vacuum pumps for an experiment, we would love to have you on the show. And if you would like to reach out to us, you can reach us a few different ways. The first being our email. We are hyperthesispodcast@gmail.com. You can reach out to us with questions or comments, or again, if you are an expert in your field, we would love to have you on. You can also reach out to us on Instagram. We are at the Hyperthesis. We post updates of when we post episodes, as well as if we need to take a break, or if we have, I think, only missed one episode apart from our breaks uploading it. So check us out there. We also do occasionally post memes. I don't know if one has been posted recently, but you can certainly keep an eye out there, and you can find us and reach out to us on Instagram. We are also on YouTube. So if you just search Hyperthesis Podcast, we will pop up on YouTube, where we are pretty much up to date with all of our episodes. You can listen to some of our episodes with guests, or the ones without guests as well. We talk about a host of different topics. So give us a like, a subscribe, or comment if you would like to hear about a certain topic in the sciences. You can find us pretty much wherever you get your podcasts. We are based out of Spotify, but we can be found on YouTube Music, Audible, Apple Podcast, or pretty much, again, wherever you get your podcast. And if you have the opportunity, please give us a rating, whether it's a star rating or leave a review. We love to read reviews, and we also love to receive feedback, especially if you do have a suggestion for a topic. So contact us however you prefer. Like, subscribe, comment, and again, if you are an expert in your field, reach out. We would love to have you on the show.
Thank you very much, Patrick. And now our story from Pheely.
So today, it's going to be a story about, I would say, one of our most, or arguably the most successful space probes that we have ever sent, because the Voyagers are the ones that are now in the interstellar space, if I remember correctly, and where it's outside of our solar system, and I think it is the first one to do so. So there are two probes, the Voyager 1 and Voyager 2, and it was launched in 1977, so quite a few years ago. So, it's in 2077, it's going to be 100 years from there. Wink, wink. So one thing that surprised me was that Voyager 2 was launched before Voyager 1. But Voyager 1 is ahead, because the Voyager 2 is planned to have the slower and longer trajectory than Voyager 1. So Voyager 2 was launched from Cape Canaveral in Florida in August 20th of 1977, and Voyager 1 lifts off a couple weeks later on the 5th of September. But in the asteroid belt, the Voyager 1 was planned so that it overtakes Voyager 2. But Voyager 2s will have different trajectories and hence different photographs and data and signal they can send back to Earth. So on the 18th of September 1977, quite a little bit, just a month or so after the launch, Voyager 1 photographs Earth from 11.7 million kilometers away, and is the first time that Earth and Moon have been seen or photographed in a single frame from a spacecraft. So you can see both Earth and Moon that, they're real and orbiting each other after all. And in January 1979, almost 2 years later, the Voyager 1 got to Jupiter from quite a bit away, 57.6 kilometers away, and it makes the closest pass for Voyager 1 to Jupiter. And the Voyager 1 and 2 saw new moons, rings, and the magnetosphere of the Jupiter to really prove that this planet is really big, red giant, and spinning. And in March that year, volcanism or the volcano activities are discovered on the Galilean moon Io, which is orbiting Jupiter. And actually, I learned a little bit about Io. That is, the volcanic activities are from the tidal force of Jupiter. Imagine the tidal force, like the tides are so strong, it stretches the moon, back and forth. The Io back and forth, that its core is not super stable, being stretched out a lot. So it has these volcanoes and volcanic activities on the moon just from the tide of Jupiter alone, because they are very strong and even destroy like comets that come around by being stretched from these tides. And a little bit later, around a year or so later, Voyager 1 got to take a look at Saturn's moon Titan, and found out it's not as large. And so the largest moon in the solar system becomes Jupiter's Ganymede. And in the November that year, the next day, Voyager 1 sails past Saturn, and Voyager 2 they both confirm that the planet's famous rings are neither solid nor liquid, but they are rings of thin aggregations of ice fragments. So they're not exactly asteroids it's a combination of water and ice, or liquid water and ice in a sense. So, and then a few years later, 6 years later, in fact, Voyager 2 encountered Uranus, which is a very bland planet, basically a little pale blue planet. So they call it the ice giant because they really look like matted pool ball. There's nothing on it. Then a few years later, the Voyager 2 became the first probe to visit Neptune. And it also turned out to be the ice giant. We have these photographs that got sent back to us. And they found that the Neptune has partial rings and the strongest wind in the solar system because the Neptune spins very, very fast. And also, a few years later in 1990, or actually a year later in 1990, Voyager 1 turned on one last time into the solar system to take a family portrait of our solar system. We are just a bunch of dots, and Earth is a pale blue dot. And then in 1998, 8 years later, Voyager 1 overtakes Pioneer 10 to become Earth's most distant human-made object in space, 10.4 billion kilometers from Earth. And Pioneer 10 was the probe that we sent to Jupiter. The mission is to go to Jupiter. And in 2012, Voyager 1 becomes the first craft to enter interstellar space. But NASA determined this 13 months later after this mass ejection from the sun, this corona that came out, which made us lost contact with the Voyager because, the electromagnetic storm kind of jam our signal. So a few years ago in 2018, Voyager 2 also followed the first one to become the second man-made object to leave the solar system. Well, it will be around 40,000 years before it encountered another star. But the actual short story from today is how Voyager 1 got kind of lost. We thought it got broken and there's some issue with it, but we fixed it, which surprised me. So Voyager 1 lost contact in the November of 2023 or of last year. And it turns out the data transmission, which usually send back photograph or signal from the solar system or the outer space, are intelligible or unintelligible. So just bunch of scrambled gibberish. So they were trying to figure out what happened there. So after months and months of testing, they found that there's a ship that's responsible for basically collecting and sending or collecting the data and processing it and before sending it to Earth. That specific ship is broken. So how they fix it is really fascinating. So that's really, you can't fix the ship because the probe is very far. So what they do is sending the signal, telling it to split up the code that runs on the ship into different ships, like multiple different ships, basically splitting up the task of that one ship into the existing ships to do that instead. So it takes about 22.5 hours for the signal to travel 24 billion kilometers out to Voyager 1 and come and the same time back. So we didn't receive message back until 20th of April, where basically these coders and engineers tell the Voyager to not use the damaged ship and use other ships to perform the same task. So they got the usable data from Voyager 1 for the first time in 5 months. So we really got the Voyager 1 back to be active again on duty. And it turns out Voyager 1 is near its end of its lifetime. To be fair, it's been around since 1977. So its battery or its power sources are running out, projected in around 2025 or 2026. So we may lose our first probe that we send into interstellar space and might not get anything from it for forever. So this might be the last few years that we're gonna have data on what it's like or what's out there in the interstellar space outside of our solar system. So this is the story of the Voyagers, and might be the last time we hear from it.
Well, thank you very much for that, Pheely. It's absolutely mind-blowing to me that even problems that happen so far away from us, these scientists are able to actually fix and sort out. That's pretty wild. And it's also pretty wild how long the Voyagers lasted for, because I'm sure that it wasn't meant to last this long. They probably only planned for it to survive a year or two, or even less, probably. It's hard to say.
No, more, because it take more than a few years to get to like the outer planets.
Yeah, but yeah, sorry, I was thinking of the Mars rover, actually. A little different. The Mars rover, one of these famous ones, they're like, oh, it'll last a month or so, and it's been going for years and years since. So a lot of the time, they engineer these things so well that they outperform way more than you would ever expect. So it's pretty amazing.
The fact that they sent out the code to fix something that's 24 billion kilometers away and successfully did it make me think it's like, well, when someone can't fix your computer, you're like, man, we fixed a probe that was launched in 77 from our solar system, and you can't fix my computer?
Exactly. Pretty amazing. But anyway, thanks everybody for joining us. This was episode 83, and we'll see you in the next one.
Take care.
Bye, everyone.